You ready to go, Lily? Great. So good morning, everyone. Welcome to the fifth of the joint data science seminars that we're holding with the Institute of Statistical Mathematics. My name is Kate Robson-Brown. I'm director of the Jean Golding Institute at the University of Bristol, which is our University Institute for Data Science and Data Intensive Research. And it's a real pleasure to be introducing our speakers this morning. We have two, both from the University of Bristol. So beginning with Patrick Rubin-Delanchy, who is a senior lecturer in statistical science here in Bristol, who's going to give us a talk on manifold structure and graph embeddings. And then we'll hand over to my colleague Song Liu, who's a lecturer in statistical science, for his presentation on estimating density models with truncation boundaries. So we'll start off, I'll hand over to you, Patrick. Thanks very much.
Thanks very much, Kate. All right, let me try to share my screen. Okay, that's kind of... Okay, can people see my screen?
Not yet, sorry.
I know. No, I just tested it a second ago, right?
It was working earlier.
Yeah. Right.
There we go. That looks better.
It's better. It's not the slide I was expecting, but right. Let me just start again. Okay, can you see that?
Yeah, that's perfect.
Okay, and I'll just put it into slideshow mode. Okay, right, can you see that?
Yeah.
Okay, perfect. And you can see my mouse too?
Yeah.
Perfect. Right, sorry for that glitch. And so thank you everyone for coming to this talk. I hope you can now hear me and see my slides okay. And before I sort of jump in, let me just take a moment to make a few acknowledgements. So the bulk of the mathematical analysis here is joint work. It's a long-term collaboration with Carrie Preeb from Johns Hopkins, Min Tang from NCSU, Joshua Cape from the University of Pittsburgh. But when we get to the data and applications, I would say they're principally from Microsoft, basically, and chiefly that's Melissa Turcotte and Anna Bertiger, but there are many others involved. I'll only have a brief chance to talk about some significant extensions, but I'll acknowledge the people involved nevertheless. So Andy Jones, Ian Gallagher and Alex Modell have all been working on sort of building from simple graph analysis to more complex graphs with me at Bristol. Okay, so I'm conscious, of course, that the audience here has quite a broad background, and with that in mind, I decided to structure my talk into three parts. The first part really is designed to be really highly accessible, hopefully. I'm just going to talk about inference based on graphs and networks, some motivations, at least for my own research program, and some fundamental challenges. Next up, I'm going to talk about estimation theory or spectral embedding. So we'll be principally extracting a few brief take-home messages from this paper with my collaborators. So it's a paper that's in second revision at one of the main stats journals, and roughly speaking, what it does is it tells us how precisely we can estimate things about nodes given their connections, right? And it represents a culmination of something like 3 to 5 years of research. So obviously we won't go through it in detail, but I'll just give you the main highlights. And then we'll go on to what you could call the main topic, I suppose, because it's the title of a talk. It's so it's content from this paper, which was very recently accepted in NeurIPS 2020 as a spotlight paper. And what this paper gives is a model-based rationale, basically, for expecting and therefore looking to find low-dimensional, hidden manifold structure in high dimensional graph embeddings. Okay. So we'll go on to our first topic then, this background section. Okay. So one of the problems that motivates research into large-scale graph inference is cybersecurity. I'll give you an example from my own research, I published a year ago. What you're looking at here is a network of authentications, basically. So each link is a user logging in from one computer to another. This is Los Alamos National Lab, so it's a big defense research lab in the US, and it has very serious cybersecurity concerns, so serious that they literally hire people to hack into their networks, right? And what you see in pink here is a highlighted red team actor, so someone who's pretending to be a malicious actor, and this gives one of the only sources of labeled malicious activity in cybersecurity networks, right? And the problem, the statistical problem, is somehow in this sort of complex network to somehow highlight or detect activity that sort of stands out as being abnormal. Okay, so that's obviously one reasonably important application. And the other sort of more nascent application, for me at least, although it's kind of well established in other groups, is anti-human trafficking, right? So DARPA in particular started this MEMIX program in 2014, which indexes the deep web for content that they believe might be related to human trafficking, right? And in particular, they generate very, very large graphs on tens of millions of ads that connect images of potential victims, phone numbers, locations, working names, and more. And the inference problems there are, you know, locating victims, for example, or identifying ads that are likely to describe trafficked individuals. Right? And I highlighted one paper here, Fishkind and al. In 2015, just because, well, I've highlighted that it was published in the Annals of Applied Statistics, right? So there is established statistical work on graph inference for this problem. Okay, so these are two applications which kind of motivate the sort of research questions that we're going to be looking at. Okay, so as I alluded to earlier, I'm just going to briefly now try to explain why graph inference is hard, basically, in various senses, or computationally and statistically. One point is that real-world graphs or networks are generally expected to be sparse, right? And what that means is, as the network grows, it's anticipated that a node's degree or its number of connections is not going to grow linearly in the number of nodes, right? So as the Facebook network went from 100 individuals to 1 billion, every node in that network didn't suddenly multiply their connections by, you know, 100,000, right? And in general, it's widely thought that the number of friends that you would make is somehow bounded, or maybe just grows very, very slowly in the size of a network. Okay. So this is a phenomenon that's believed to hold about real-world networks, and it imposes information theoretic limits on what you can actually infer about the nodes. Right. And these results are usually framed in terms of network community recovery, right? So what sort of community structure can I hope to recover in a network if it is very sparse? Okay, I know this slide looks a little bit mathematical, but hopefully if you just listen to me, it will all be reasonably clear. So to put down a community-based network model, you need a concrete model, of course, and the model uses a stochastic block model. And I won't go into the details of it, but basically what it does is it puts down a partition of the nodes. It kind of assumes the nodes can be partitioned into groups. And then there are just probabilities that give you the chance of a link between any two groups, right? So if you only have two groups, and all you have is a probability that an individual from group 1 would connect with another individual from group 1, the probability that an individual from group 1 would connect with an individual from group 2, and the probability that an individual from group 2 would connect with another individual from group 2. So you've only got 3 probabilities here. And in fact, in these information theoretic analyses, they simplify it even more by assuming that you've got a symmetric two-community stochastic block model, in which case you're imagining the communities are the same size, and there's just an inter-community probability and an intra-community probability. So these probabilities A and B. Okay, the picture in terms of detectability is kind of very complex and very rich. And I'm just going to summarize really something that's a lot more complex in these two results, which are summarized in ABE 2017. It's a review paper. Basically, if degrees grow logarithmically, you can expect to recover the community structure perfectly, or almost perfectly in a mathematical sense. Not only that, but spectral methods, which are the methods we're going to be looking at, will work, right? They won't work if you just use what we use, but they will work with very trivial adjustments. Right? So in the exact recovery regime, the one where the degrees are growing logarithmically, you're in a good place because statistically you can estimate what you want to estimate, and computationally you can estimate what you want to estimate, because spectral methods are polynomial time. The picture, if the degrees grow less fast, is much harder, basically, much less conclusive. In particular, if the degrees don't grow at all, if you stay fixed, you can get so-called weak recovery, right? So you can still, for example, tell that there's some community structure present, even though you can't perfectly assign everyone to their community. But direct spectral methods no longer work, right? So if you're in a very, very sparse regime, it starts becoming, well, statistically very difficult, but also computationally very difficult to say anything. So that's one of the really fundamental barriers of a task we face. You know, if a graphs are very, very sparse, it's very difficult to say anything statistically or do anything computationally. And the other sort of common problem we have to face is this notion of high dimension, right? So nodes in real world graphs are generally thought to be high dimensional. Right? I mean, that, you know, it's a very vague statement, but it can be made precise and has been made precise in the following way. If you're trying to somehow represent the nodes as vectors, right, as points in space, and you're using an inner product based representation, which would be common, and is fundamentally what's been done in spectral embedding and node-to-vec, which are two of the most popular techniques, you would effectively need an infinite dimension to capture the most commonly observed properties of real networks. Right? So in that sense, at least, it's generally believed that nodes are, if not infinite dimensional, certainly very high dimensional. And statistics in high dimension is very difficult. So anyone who's from the statistical background will know this, of course, but things like estimating a density become exponentially hard in the dimension. And things like regression, so classifying nodes or detecting things about nodes, also become exponentially hard with dimension. So if you're in high dimension, I mean, you're not at any sort of information limit, but you certainly are at various sort of statistically unfavorable regimes. Okay. So that was my brief, highly accessible background. And now I'm going to talk in more detail, after having told you all the reasons why spectral embedding is going to suffer. I'm now going to tell you everything about spectral embedding. So to be concrete, right, we're imagining, at least for now, that we have an undirected graph. And we're going to represent this undirected graph of a binary symmetric adjacency matrix A. Right? So Aij is 1 if nodes I and j have a link, and is 0 otherwise. The spectral embedding, it comes in various flavors, right? I'm just giving you the simplest one. What you do is you work out the spectral decomposition of A. All right? So you work out its eigenvectors and its eigenvalues. you put the eigenvectors of A inside this U matrix, which is an orthonormal matrix, and the eigenvalues into a diagonal S matrix, and that gives you the so-called spectral decomposition of A. And if you just pick out the D columns, both of U, and the D first entries of S, and construct this matrix U S a half, then you get the so-called spectral embedding of A. Okay. So what we end up with is, starting with a graph, a D-dimensional representation of every node in the graph, right? And each of these points, x1 up to xn, are these D-dimensional representations of the corresponding nodes. Are there any questions? I don't have access to the chat, so if there's nothing burning, I'll keep going. I'll just give.
Not yet, Patrick.
Okay, great. Okay, so that's spectral embedding. If you're about to use my slides and actually implement spectral embedding on the basis of them, I should mention, of course, you don't actually in practice go and compute all of the eigenvectors of A, right? Because all you need is the first D of them, right? So you'll use an R package, for example, that will specifically only compute the first D eigenvectors of a matrix, right? And that will be much faster. And in general, I would say spectral embedding is one of those techniques that you can hope to use on any scale of graph, right? So there's nothing to fear about a graph that, for example, has 1 million nodes. Okay, so just as an example, I mean, if you simulate a graph from a stochastic block model, so a community-based graph, and in this case, there are only 2 communities. And you then spectrally embed that graph according to the recipe I just gave. This is a point cloud you'll get, right, if you choose D equals 2. Right, so we're spectrally embedding a simulated graph into R2. And you can see, hopefully, that there's cluster structure there, right? And you might hope, of course, that these clusters correspond to communities, and they do. And that's why we say you can use spectral methods to recover communities. I mean, what we really mean is you use spectral embedding followed by some clustering algorithm. And that clustering algorithm will recover asymptotically the correct partition of the nodes, or at least will be correlated with the correct partition of the nodes. Okay, so that's the spectral clustering algorithm, basically. And to give you a single slide that essentially summarizes something like 5 years of research, this is it. Under some compatible definition of true positions x1 up to xn, that we're going to claim these x hats are kind of estimating, the following convergences are true, right? So first of all, if you look at any particular position on its own, right, it's asymptotically Gaussian distributed, centered about the truth. Okay. Now you'll notice there's a couple of terms that I'm not explaining here. So square root of n is a necessary scaling for that Gaussian limit to emerge. There's a matrix Q here, which is just applying some sort of distortion, which we understand more and more, and which doesn't affect inference too much because it's well behaved. So for example, if you're doing Gaussian clustering, the presence of some linear transformation that's applied to all of the points together doesn't actually change results, as long as that linear transformation is invertible and has some bounded condition number. The second result is the so-called 2 to infinity norm, and it's a convergence result that concerns all of the nodes together. And basically what it says is, after this distortion by Q, the maximum error across all of the nodes goes to 0, right? So as n goes to infinity, you're going to localize every single position in space perfectly in probability. And these results, or certainly the second result, kind of tell you why you might expect perfect recovery under the stochastic block model. Because basically what's going to happen is all of the estimated positions are all going to converge to a single position, and that single position is actually representing the community. So just to show these results in practice, On the left over here, you have a raw embedding. Our results tell you you should be trying to fit a Gaussian mixture model to those. And the middle picture is what you would get. And on the right, you have what the theory is predicting, basically. So you've got some distortion, some linear transformation Q that's kind of flipping the picture. So suddenly the red cluster is on top and has a slightly different shape. But after you've done this distortion, you can see that the theoretical ellipses, which are in solid, roughly align with the estimated ellipses, which are in dashed. Okay, and I'm just going to have time to briefly talk about some extensions of this work. So this first extension is by Andy Jones, who's doing a postdoc here at the University of Bristol with me. And he's been looking at trying to extend the theory, which has not been in any sort of way trivial, to the analysis of multiple graphs, right? So this is an ATI project. And you might hope, basically, in a lot of these applications, like anti-human trafficking, you will have different graphs connecting the individuals differently. And what we're able to do is, for example, even with graphs that have very different structure, so the first graph here is going to have assortative behavior, so things that are similar tend to connect, and the second graph is disassortative behavior, so opposites attract, and the last one has this core periphery structure. You can bring these graphs together and apply the same sort of techniques and get a much better joint embedding, right, which is shown on the right. The other extension is by Ian Gallagher, who's doing a PhD here at the University of Bristol, and it's about trying to do the same sort of analysis of weighted graphs, right? So here in particular, this is an experiment we did with Microsoft. You're going to get anomaly scores between nodes on a cybersecurity network, on a cyber network, sorry. And they happen to have access to some nodes which they know are malicious because they're actually red team hired. And those malicious nodes are in red in both pictures. And what Ian has been able to demonstrate is that some representations of the p-values are better at separating the anomalous clusters than others, right? In particular, taking the log p-value seems to be a good idea. And finally, this is work with Alex Modell, who's just starting a PhD under the Compass program, and he's looking with others at the extension to multipartite graphs, right? So when you have graphs that connect, for example, objects of different type, like well, web ads and addresses and phone numbers, for example, or in this cybersecurity example, you've got users, computers, and processes. Can you use the same sort of technology to get a joint embedding that somehow uses all of these graphs together? Okay. So as I said, I've only got time to go through these examples quickly. Okay, so on to section 3 then, which is kind of a main event. You might have noticed a bit of a discrepancy between the pictures I show that correspond to simulated graphs and the pictures, the spectral embeddings I show you of real graphs, right? And the difference is, well, is not too unfamiliar. It's basically that the simulated graphs tend to generate much more regular pictures. But one sort of more significant problem maybe is that it's a very specific sort of regularity in that spectral embeddings of graphs following a stochastic plot model have a simple pattern of K clusters. They show these very clustered configurations. Whereas you could claim that in the real spectral embeddings, you're observing something much richer somehow. And so this work is about starting to think about more interesting geometric analyses of spectral embeddings than just clustering. So I'm going to show you the most tenuous picture of his talk. And it's basically a visualization of 4 different large graphs, which is obtained by spectral embedding, followed by t-SNE. So I'll just go through each of these graphs briefly in turn. So in the first graph, what you have is internet traffic on the Los Alamos National Lab network. What you do is you spectrally embed the graph into 10 dimensions, and then you squash it into 2, basically using this technique by Matten and Hint in 2008. And it's clear, right, that this squashing can do all sorts of unknown and perhaps slightly misleading things. Nevertheless, so in order to really validate the structure you see, what I've done is I've colored the nodes according to completely independent information when that information is available. So in the first picture, the color is the sort of port that you tend to use, right? And the port you tend to use indicates the sort of traffic you're typically involved in. So I seem to remember that yellow, for example, is web activity, port 80. And I think light blue is 445, which is file access. And I think, I'm not sure about that. So. In B, you have an authentication graph, actually very similar to the one I showed at the beginning of the talk. And the colors are basically indicating the authentication type. Again, it's just to show that the structure you're seeing isn't completely made up, right? It is correlated with independent information. In C, it's a completely different application. It's we're embedding restaurants, basically, on the basis of customer ratings. And the color here is the state that the restaurant is in the US. So green, I think, is Arizona, for example. And D, we didn't have colors, unfortunately, for this example. This is the MEMEX program anti-human trafficking graph, right? So this is a graph of web advertisements sort of collected from the deep web. And some of them thought to pertain to potential human trafficking victims. And adjacency here in the graph is basically a shared phone number or address region. Okay, so why am I showing you this picture as well? What I'm trying to demonstrate, and I know it's very tenuous, is that there seems to be some benefit to finding low-dimensional structure in these sort of higher dimensional embeddings. For example, the pictures I would have shown you if I just went for a two-dimensional spectral embedding would have been much less rich. Right? And for years, basically, I've been trying to understand why that is. Right? Now, I'll mention that the hypothesis somehow that low-dimensional structure is present in high-dimensional data is a very important hypothesis for machine learning. Right? And in some, I mean, it's sometimes really held to explain why high-dimensional learning is even sort of realistically possible, right? How deep learning, for example, can have as good results as it does. And in particular, I know at least one of these offers at least has some connection to the ISM. These offers have shown recently that if you apply deep neural network regression on high-dimensional data of low Minkowski dimension and sort of bounded smoothness, you will actually get an estimation rate that is consistent with the intrinsic rather than ambient dimension, right? So there are really significant advantages to exploiting manifold structure if it's there, right? Because it's basically a form of dimension reduction, right? Which is the most important advantage you can have in statistics, typically. So really what the rest of this talk is about is to try to justify the application of manifold exploiting techniques on graph embeddings, something that empirically works, by finding a model-based rationale for why manifold structure might be present. Okay, well, this is sort of a punchline in a way. I mean, the reason manifold structure might be present is because the graph might follow a latent position model, right? And in very broad terms, what a latent position model is you somehow imagine that the nodes have a vector representation in finite dimension, and then that the links are formed just as some function, a kernel, of the two latent positions of the corresponding nodes, right? So to give a sort of ridiculous example, you could imagine that the Facebook graph was only constructed through the positions of all of the individuals on Earth, right? So in this case, everyone would have a 3D position on Earth, which would live on this two-dimensional sphere. And then some function over positions might give you the probability of a link, right? So latent position models have existed now for some time, and there's really quite a lot of mathematical analysis of them. And I'm putting it out there that if we believe that some form of latent position model is generating the data, then there is good reason to believe that spectral embeddings will have this hidden manifold in them. So let me just give you a simulated example to make that point a little bit more eloquently. A very commonly used latent position model, or certainly one that was used in a red paper in the Journal of the Royal Statistical Society by Kernel and Fox, is this sociability kernel, right? So this is a very simple model in a way, and unrealistically simple perhaps, where you just imagine that connections occur as a function of people's sociability, right? So you have sociable people and you have antisocial people, right? And how social you are is just represented by a number, a scalar on R, right? So if that scalar is large, you're someone who makes a lot of connections, and if it's small, then you're someone who doesn't like making connections. And this kernel F is just a function of the two sociabilities, right? So 1 minus exponential minus 2xy. So generate a graph from that kernel, a latent position model. So generate a graph that follows that latent position model with that kernel. Spectrally embed it. Pick the first 3 eigenvectors because we can't look any further visually. And this is a picture you'll get, right? So the black dots are the embedded nodes, and the blue line is a sort of theoretical manifold on which they live. And this picture is certainly suggestive somehow that this hypothesis is true, right? That the data somehow, even though they live in this case an infinite dimension, they're actually all very close to a much lower dimension manifold. In this case, it's just a 1-dimensional manifold. Okay, so this is sort of like where it gets a little bit technical. I'll just give you just a flavor of the techniques that need to be used without going into too much detail. You have to go into operator theory. And what we're basically going to try to do is find some sort of map, which you might think to be analogous to a feature map, which is going to take a latent position in this latent position model and map it to a higher dimension into a new position that lives in high dimension that we're going to claim is being estimated by spectral embedding. Right. We need to make a few assumptions, and probably the sort of most important one is this trace class assumption that somehow the spectrum of this operator is bounded in the sense that the sum of the spectrum of its operator is bounded in a sense that the sum of its absolute eigenvalues converges. That's probably all I need to say about this. Really, all we've done here in this analysis is somehow try to construct a map, right, from a latent position that we're calling Zi, which lived in the original low-dimensional space, and through which links are generated by this through this kernel. We're trying to generate a map from that latent position into like a higher dimension latent position xi, which is the target of estimation by spectral embedding. Now, we've already seen how spectral embedding does at estimating these high dimensional vectors, right? And for example, we know that at least in finite dimension, those embedded positions are going to be asymptotically Gaussian, and we also know that they're going to be strongly consistent in the sense that the largest error over the whole group is going to shrink to 0. And really all that we need to prove now is somehow that the map, which goes from this low dimension to this high dimension, is regular enough that it wouldn't change dimension, right? You would like the map to just generate some distortion of original space that lives in this high dimensional space, but actually just has this low dimensional manifold structure. Okay, so what do we mean by dimension? You need to settle on some notion of the dimension of a set. The one that works for the maths here is a Hausdorff dimension, right? I mean, I only really have time to go through this briefly, but what you can imagine is you take a set and you basically come up with a cover of that set. So you fit balls, for example, to cover the set, and you look at the volume of that cover, and you try to make that volume as small as possible and still cover the set. And you look at how that shrinks. And if it shrinks as would an object of dimension 1, then you say that that set has dimension 1. And it typically gives you the sort of answers that you expect. For example, a curve will have dimension 1, a cube will have dimension 3, etc. Anyway, for this definition of Hausdorff dimension, and under this assumption that somehow the curvature of a kernel is bounded on its diagonal, we have the theorem that we're looking for, which is that actually, yes, what you've got here is a set living in high dimension, but with an intrinsic dimension that is just the original dimension of a latent position model. Okay. So this is just a quick slide to demonstrate that our results are, in a sense, very weak. Right? I mean, we've used the word manifold because that's what's done. But really, we haven't proved that what we have here is a Riemannian manifold, right? Well, all we've proved really is that we have a low-dimensional set, right? And for example, you can work quite hard and start finding examples where your set is one-dimensional, but it has a branch point, right? So that's what happens in the middle picture. You can also work. It's a little bit less hard to do this, but you can also find an example where your set, which started as just something like the Kernel model, now just becomes a circle in high dimension, right? So what we know topologically or even sort of geometrically about the set is very little, right? But what we do know is that it has low dimension, and it has, under the assumptions I gave, the same dimension as the original latent position model. Okay, so just a couple more slides just to give you a few promising applications. I mean, the first one's for graph regression. So if you want to predict something about the nodes, if in cybersecurity or anti-human trafficking applications, you've been given some information about some of the nodes. For example, you know that some of the nodes are malicious. You might be interested in spectral embedding and then applying a standard classification tool, right? Now, because you're typically going to be needing to work in very high dimension, you would have no reason to think you do very well at this exercise, right? But our results suggest that actually you might do much better than you might originally have thought. And you just have to use the right tools, basically. So if you use a random forest or a neural network, two machine learning classification tools which are known to exploit hidden manifold structure, then this picture shows that actually you can do really quite well. You can do almost as well as if you actually had the original latent positions. If you use slightly more naive approaches which don't try to exploit hidden manifold structure, you won't do nearly as well. And just to sort of show you the state of the art, just because I kind of find these pictures funny, if anything else. And if you want to take this further and try to actually start estimating manifolds, for example, so you can estimate the original latent position model using spectral embedding, then you suddenly challenged with the fact that manifold estimation is itself an extremely difficult problem, right? And you can see here the sort of state of the art in manifold estimation, which is ridge estimation. So it does quite well, I guess, in the first picture, but in the second picture, you have this sort of very interesting estimate, right? The red line is what's estimated, which kind of captures some of a topology, right? But it's really kind of quite far from the truth. So I think that's it. Yeah, thank you very much.
Great, thank you, Patrick. We can open up for a few questions. We've got a good turnout this morning. I can see 43 of us and lots of names I recognise. So do put a note in the chat, or even just put your hand up and I'll come to you. We can't let Patrick get away with it that easily. Patrick, I can ask you a kind of general applications question. So I have a personal interest in the kind of humanitarian side of things, and I'm interested in your kind of developing ideas around anti-human trafficking. Where do you think you could take that next?
Yeah, well, we're trying to figure that out basically with Microsoft, right? So Microsoft took, had a sort of big role in this MEMICS program, which was I think technically DARPA, and they have access basically and have helped build these very large knowledge graphs, which connect traffickers and victims and whatever else. The problem really in that area is data sharing, right? I mean, cybersecurity is problematic, but anti-human trafficking is even more so, right? I mean, so really it is verging on inconceivable, really, but you'd ever get to a stage where you could really go there and actually analyze the real data. I mean, you'd have to start working with law enforcement and stuff, right? So we're trying to build at least some sort of bridge, right, to try to get these methods maybe working on some restricted prototype graphs, right? And one of the graphs I showed today is an example, right, which is publicly available. But yeah, I mean, to take this to a place where we could have real impact and really change things, right? I'm not sure, it's work in progress.
I'll maybe talk to you offline about that. Might be an opportunity. Kenji, I can see your hand up. Go for it.
Hi, Patrick. Thank you for your very interesting talk. And I have a question on the manifold estimation. How did you decide the dimensionality of the manifold?
So we cheated and assumed we knew.
Is there any good way of estimating their dimensionality based on their eigen decay or the distribution of the eigenvalues?
No, basically it's a mistake, I believe, to look at the rank of the matrix or the spectrum of a matrix to judge what the manifold dimension is. To look at the spectrum of a matrix, what you'll get is basically the ambient dimension. To try to get an estimate of the manifold dimension, there are a few techniques actually, and the authors I referenced actually, one of them was Nakada. In their paper on deep learning on manifolds, they use something like 3 different methods that exist at the moment to try to get an estimate of intrinsic dimensions. So there are already sort of tools that you can just use to do that. I don't exactly know how precisely they work for the error models that we know are present in graph embedding. But certainly there are existing tools that will try to estimate the manifold dimension if you give them a sort of high dimensional point cloud, as I'm sure you know.
Okay, thank you.
Okay, great. I don't see any other questions right now. We're bang on time. So it's be a real pleasure for me to introduce our second speaker. Song Liu is going to give us a shorter talk this morning. Just to remind you, Song is a lecturer here in Bristol in statistical science, and his talk will be on estimating density models with truncation boundaries. Over to you, Song.
Thank you very much. First, let me share my screen. Oh, by the way, So the slides of my talk is available at this link. If you're interested, you can download it and see it yourself. Okay, can everybody see my screen?
I can. Yeah.
Okay, cool. Okay, so in the next 15 minutes, I'm going to give a very brief introduction of my recent research on estimating densities with truncation boundaries. And first of all, I'd like to acknowledge my excellent co-workers. They are Professor Takafumi Kanamori from Tokyo Institute of Technology and my PhD student, Daniel Williams. And well, saying this is a brief introduction, perhaps I've introduced a little bit too much technical detail in the slides, but don't worry, if you want to know more or you missed some details, you can always find our paper on arXiv and also our code to reproduce our results on GitHub. Okay, so let's begin by talking about truncation. So in many cases, our observations are truncated. For example, in the police department, usually the police department can only observe crimes that is happening within the city boundary. But as we know, crimes do not just stop at an artificial border. For example, this is a Chicago crime dataset where you can see the blue dots are crime locations, homicide crime locations happened in Chicago in 2008. You can see when I plot these observations over the boundary of Chicago, these observations are naturally truncated by the boundary of Chicago. And you don't see any crimes that is beyond the boundary of Chicago. So that is a typical case for truncated observation. We can't see beyond the boundary. There is actually another really interesting example recently that is a number of positive COVID tests, because the number of tests we can do per day is also capped. So our observation of the positive test results is also capped. And this is also another example for a truncated observation. Just, naturally, we have all these restrictions when we are trying to observe our data set. And therefore, these observations sometimes are truncated. And we can only see through a limited window. And not just data sets sometimes are truncated, but some density functions are also naturally defined on a bounded domain. For example, Dirichlet distribution. And in this case, this distribution is only defined on a probability simplex. It is also a bounded domain. So if you generate Dirichlet samples, you can see all those samples are always bounded in this triangle region, in this three-dimensional space, not all over RD. Okay, so these are examples of truncated densities and observations. Let's introduce the task here. The statistic task we want to do is density estimation. To estimate the density, we need a parametric model. So here we define the density function on a truncated domain V, that is a subset of Euclidean space RD. And naturally, this density model can be written as a ratio between P bar and ZV. This P bar is unnormalized density function parameterized by parameter theta, while this ZV is a normalization term that helps our density function to be normalized over the domain V. And therefore, this ZV is not arbitrarily chosen. It is defined as an integral of our unnormalized part of the density P bar over the domain V. Okay, and this is a very generic definition for the density function over truncated domain. And you can find many examples that follows this definition. And here the task is to estimate density function. So given a set of data points xq from x1 to xnq, and all those x are in truncated domain V, we would like to fit a density model, a truncated density model, to our data set xq. So this is our task. You might think it is a very simple task because density estimation is a very classic problem, and we just apply some classic methods, such as maximum likelihood, to solve the problem. The caveat here is that our truncation actually introduces the intractability in our estimation problem. If you look at the ZV, the definition of ZV, it is an integral with respect to a complicated domain. Therefore, this integration may not have a closed form expression. And in maximum likelihood, you are required to evaluate such a normalization term, which cannot be easily applied here. This is the problem. So what's the solution? The idea is actually really simple. We just define an estimator that does not requiring evaluating this intractable normalization term. And luckily, there is such a method, can estimate density function without evaluating the intractable normalization term. And the method is called score matching. And the score matching was proposed a long time ago by Hivarian and collaborators and handles unnormalized density models. The methodology simply minimizes the Fisher divergence between our model density and data density in terms of L2 norm. And you can see this divergence is virtually just the L2 norm squared between the gradient of our data density and the gradient of our, gradient of our model density and gradient of our data density. And the procedure or this algorithm can be intuitively understood using the visualization below. So for example, we have data points here and we have data density here, and score matching basically match the gradients of these two density functions, the data density the gradient of data density function and the gradient of our model density function. And you can intuitively see that the gradient of your density function is not at all affected by normalizing constant, because you are just simply dividing normalizing constant as a constant. So it doesn't change the shape of your density function. And if you want to look at this problem more algebraically, you can see whenever you take the gradient with respect to the log density function, the normalization term is eliminated because the normalizing term is a constant with respect to our input x. So when taking the gradient with respect to the input, it is eliminated. Now the score matching function does have a very simple and intuitive objective. And if you expand the square, you'll get three different terms: the quadratic term, the cross term, and a constant that does not depend on the parameter theta. But there is, again, a small problem here. The small problem is that this cross term is not straightforwardly tractable. I mean, this cross term, it requires the gradient of the log data density function. And we do not have access to this gradient of log density function, log data density function. So we can't directly evaluate this term as well. So what's the solution? In score matching, we apply a lemma. And this lemma allows you to convert this term into a different but tractable term. So here is the statement of the lemma. Okay, the first part is if the log Q is continuous differentiable, log P theta is twice continuously differentiable with respect to X, and the limit of this product equals to 0 when Xi tending to infinity. Then this intractable term here can be rewritten in the term here. This makes big difference because now this term is an expectation of with respect to Q and of a function that only depends on P theta. Remember, P theta is our model, and we can evaluate however we want, how many times we want. So this term can be converted into a sample approximation using our dataset XQ. Therefore, our objective function becomes something like this after this conversion, and the first term doesn't change, and the cross term becomes something like this due to the lemma. And now you can see this objective function can be totally approximated using our data points in our XQ, in the dataset XQ. Okay. Okay, so let's have a second look at this lemma and look at this conversion. This lemma requires this limit condition, and this limit condition requires this product equals to 0 when x tending to infinity. You can see this lemma holds, this condition holds if your density function qx, the data density, vanishes at infinity. Well, this is reasonable for many distributions like Gaussian distribution naturally vanishes at infinitely far away. However, this condition does not make much sense if we restrict the x to a subset of Rd. Now you can't allow the x to go to infinity. How does this lemma make sense anymore? So this lemma cannot be directly applied to our cause because we are interested in a bounded domain where x cannot go to infinity. And this is the problem of the classic score matching and when applying to a bounded domain. Actually, people have been working on extending the score matching algorithm to partially bounded domain. And in this case, it is domain Rd plus, that is the positive domain. The classic score matching can be augmented to estimate densities partially bounded, that is domain Rd positive. And the augmentation is really simple. You just multiply a function g of x to our model density and to our data, to our gradient of the model density and the gradient of the data density. And then the score matching objective largely remains the same. You are still matching the gradients, but now you're kind of reweighting your gradients with a function, a spectral function gx. And gx has to satisfy the following condition, that is continuously differentiable and g0 equals to 0. And you can find many g functions that satisfy this constraint. For example, you can let gx equals to x, which satisfies this constraint very well. Again, we need to convert our score matching objective to a tractable score matching objective, because in previous case, we still have the cross term that is between data density and model density and the data density. So so in this case, we introduce a slightly different lemma, and the first half of the lemma is the same, that we require log q and log p theta to be continuously differentiable. And here, since we also introduced the g of x, we require it to be continuously differentiable as well. The minor but very important difference is now we require this product to be 0 when the limit of x is taken to 0 plus or positive infinity. Then this lemma guarantees that this expectation of the cross term can be converted to an expectation of something only involves the data density p theta. And in this case, we can approximate this term by our dataset XQ nicely. And you can also verify the condition of the lemma that if q of x vanishes to infinity and g of 0 equals to 0, then this lemma holds. And in the case of normal distribution or a truncated normal distribution, this naturally holds because the normal distribution vanishes at positive infinity, and by design, g0 equals to 0. So this lemma holds, and we can have this nice conversion from intractable cross term to a tractable term. Now we have a tractable version of the objective function. So let's ask ourselves a more complicated problem. Can we extend square matching to a more complicated but bounded truncation domain? In the previous case, we only assume the truncation happens element-wise, that is, xi on each dimension I is in this positive real domain. What about more generic, non-element-wise truncation domain? Recall the Chicago prime data set. The boundary of Chicago is certainly not an element-wise truncated domain. It is a very complex polygon. And how do we extend square matching to this specific bounded domain? So this is our proposal. Our proposed algorithm solves this minimax problem, and the objective function is very similar to the previous case. We still have the square matching loss, the difference between two gradients, and we also reweight this loss by a function g. The difference is g requires to be 0 whenever x is on the boundary of our domain V, and partial V here represent the boundary of our domain. And g is also required to be Lipschitz continuous. And it looks like a very complicated problem, but actually the inner maximization can be easily done because we can find the exact maximizer of the inner maximization problem, that is g equals to g0, which is L times the minimum of the distance, Euclidean distance between x and x prime, where x prime is on the boundary of your truncation domain V. In other words, g0 is the distance function from your data point x to the truncation boundary. Here, I plot the contour of the g0 function for different truncation domains. When the truncation domain is a circle, you have a cone. When the truncation domain is a triangle, you have this polytope. And for more complicated truncation domain, you can easily evaluate g0 as well, as shown here. So the issue here is slightly more complicated than the previous case, because again, we are facing the problem that transforming this truncated square matching objective function to a tractable objective function. So we naturally need a lemma for our g0 function. But as you can see from the plot, g0 is not continuously differentiable everywhere. So the classic integration by parts cannot be used. Okay, I'll see. Sorry, I forgot to mention. The previous lemma utilizes a technique called integration by parts. But now, since g0 is no longer a everywhere differentiable function, the classic integration by parts cannot be used. But we can prove that if V is a Lipschitz domain, then g0 function is actually in Sobolev space, which means it is differentiable outside of a measure 0 set. You can easily also verify here, this cone, only the top is not differentiable, and this polytope, only the edge is not differentiable. And these are all measure 0 set. So it doesn't actually affect the integration by part technique. So we can actually apply a different version of integration by parts on Sobolev space to derive a lemma, to convert an intractable term in square matching to a tractable term, to two tractable terms. And here you can see the first half is the same, continuous differentiable for Q and for P theta, but now we require this product to be equal to 0 when xi is evaluated at the boundary of the truncation domain. And by the definition of G0 function, which is a distance function, this condition is naturally satisfied. Okay, so how have we gotten here? So we have the classic score matching objective function proposed in 2005 that applies on unbounded domain, and the weighting function equals to 1, which is no weighting at all. And in 2018, this method has been extended to element-wise bounded domain and introduces an element-wisely designed G weighting function. And in our paper, we consider a more generic Lipschitz bounded domain where the weighting function G is also Lipschitz continuous. And we also used a slightly different version of integration by parts, that is Green theorem for Sobolev space, to prove the lemma that is required to convert our objective function. Now, let's have a look at some example. So let me just skip the previous one and to the experimental results. So here you see is a data set generated by Gaussian mixture, 4 Gaussian mixture. You can see a blob here, blob here, blob here, blob here. And the truncation domain is the green region, that is only shaded green region. So we can't see all the data points that is outside of the green region. We can only see points that is inside the green region. The task is to estimate a Gaussian mixture model, or the center of the Gaussian mixture model, using only the data points inside the green region. And the truncated SVM gives us this, this, and this, and this. Even if these center of the Gaussian mixture are outside of our truncation domain, our algorithm can still recover these centers very nicely. In contrast, the maximum likelihood estimation can only give us something that is inside the green region because it is unaware of this truncation V. And here we show a Chicago crime dataset result. So again, the task is to estimate a Gaussian mixture model and fit the Gaussian mixture model to the crime locations. And you can see the truncation region is naturally the boundary of Chicago, and data set is also inside this truncation boundary, and the red dots are estimated locations, the center of the Gaussian mixture. You can see the truncated SVM gives us the center right next to the truncation border, which explains nicely the declining rate of crime from the left to the right. While the maximum likelihood, unaware of this truncation boundary, gives us a Gaussian mixture center that is inside of the truncated region. Okay, so in conclusion, that we studied the density estimation problem with a truncated boundary by using a maximally weighted score matching objective. This extends an earlier work where the truncation domain is only defined element-wise. And experiments on real and toy dataset show promising results. Sorry, I'm a bit longer than I expected. Thank you very much for listening. And if you have any questions.
Thanks very much, Song. I believe I'm the one who's supposed to chair your talk because Kate had to leave. So, so you have a couple of questions in the chat. Would you like me to read them to you, or have you got access to them?
Yes, I can see them on my screen. So Professor Fukumitsu asked, how did you compute the distance to the boundary of the Chicago crime data? So actually, that's a very interesting question. So for different truncation domain, we have different ways to calculate the distance to the boundary. And because Chicago crime, the Chicago boundary is a polygon. So there exists a very nice algorithm to quickly solve the distance to the boundary problem for the polygon shape. This is a special case, like only exists for 2D polygon. And we also consider in our paper different types of truncated shapes, like convex polytope and things like that. And there are also polynomial time algorithm that can help you to find the distance to the boundary efficiently. How easy it is to tell the given domain is Lipschitz or not? Okay, so this is a very interesting question. The quick answer is I don't know. I just made the assumption that V is Lipschitz domain. But I think Lipschitz domain is reasonably kind of a flexible, generic bounded domain that only requires the boundary to be the graph of a Lipschitz function. So I think it's a kind of reasonable assumption, but that's a very good question. I don't know how to tell if a domain is Lipschitz or not. Peter has a question.
Hi, Song. Very nice talk. Nice work. Thank you very much. I have a small question and a slightly bigger one. It's both fairly small. Data that looks a bit like this often is not actually a random sample from anything. These look like, some of these look like spatial statistics problems where what you're seeing is a point process, which may have a first order intensity, but has dependence among the points. In the crime case, you can imagine clusters, for example.
Yeah.
It occurs to me that with appropriate modifications, your methods and your estimator might still work for that situation. Have you or anyone else ever thought of using score matching estimators in that context?
That's a very interesting question. Actually, I've been thinking about it. We were so close doing a Poisson process in this case that to fit a kind of like a count data over a region of like geographical region. The issue is Poisson process is a discrete process, discrete distribution. So score matching requires the gradient. That is not applicable, but definitely for more continuous processes, continuous distribution.
Yeah, so actually a Poisson process conditioned on its number of points is exactly a random sample. So you're already covering that case.
Right. So yeah, so I think definitely it's an interesting problem. I think so. I think we can do that using score matching algorithm. And yeah, I think that's definitely a very interesting future work to
The other very quick small thing, if you don't mind, on the west of Chicago, you've got the rest of Illinois. On the east of Chicago, you've got Lake Michigan. They're very different boundaries. Crimes can come across the west boundary, but they can't come across the east boundary.
True.
So, yeah, I guess in your formulation, those two boundaries are treated equally. Is that right? That's
a very good question. Yes. I think it's not appropriate to treat this part as a truncation. This is actually not a truncation. And this side is a truncation. Thank you very much for the comments. We will definitely take this into consideration and then revise our experiments.
Sure. Thanks.
Yeah.
May I ask a question?
Yes, please.
I worried about this. You say the introduction of G function, which vanishes at the boundary.
Yeah.
In the process, in the estimation process, the samples which is near the boundary has a smaller weight in the estimation process.
Yeah.
And I worry about it.
That's a very good point. So basically, we're discounting data points that is near the truncation border. This is one of the reasons.
Sometimes on the boundary, your data is ignored.
Yes, that's true. That's true. So that's a very good point. Actually, we assumed the G function to be Lipschitz continuous. So if the boundary is 0, the boundary evaluation is 0, then if your function is Lipschitz continuous, you always have small weights near the boundary.
Right.
That seems to be an unavoidable problem in my opinion. And I also worried about that. So I tried different family of G function, like for example, if G is like continuous differentiable function or something like that, but then you don't really have this nice Lipschitz property anymore, and you can't really use the this integration by parts anymore, because now your function is very steep, you know, like almost vertical at the boundary, and then this kind of integration by parts break down. This is like the technical reason we have to use like something like Lipschitz function as a G function. But you got me. I'm not sure how to, you know, how to solve the problem that we have like small weights for the points that is near the boundary. I think like a theoretical study is needed, like proving the consistency, which are also ongoing work, see how exactly the weights affect the estimation efficiency or convergence rate. And that would give us a much clearer picture of how G affects these results.
Okay, thank you.
Thank you very much. Okay, so Takatomi has a question. When a boundary is not given explicit, but we know there exists a boundary, is it possible to estimate it? That's also a very good question. I am not sure how to do that. We definitely thought about it. We definitely thought like if we can, you know, estimate the truncation boundary, that would be cool, right? But if you look at the data set of Chicago crime, it's really hard to estimate the boundary accurately, because you see, you don't have many crimes here. So basically you maybe you don't see there is a boundary here because you don't, you know, have lots of observations here and here. So that's a very hard, I would say even harder problem than density estimation. Yeah, but that's a very interesting thing that I'm not sure how to solve the problem though. Thank you very much for your comments. We will definitely think about it.
I'm not sure, but you might have a question also from Kenji. His hand is up, but I don't know if that's...
Oh, Fukumi-sensei, do you have a question?
No, sorry, that was the previous question.
Oh, okay.
For the previous question, sorry.
Okay. No more question, I think. Patrick, do you have a question?
I mean, yeah, I thought it was very interesting, and yeah, I did have questions, but I was going to ask, have you thought of estimating a Gaussian mixture model in a bounded domain, and then that your application came up, and that's what you were doing.
Cool.
Well, that to me seems like a really hot application, actually. I mean, so many situations, right, where you're trying to fit a Gaussian mixture model to like a square, for example, right? And so really, really interesting work.
Thank you very much. So we can talk about.
Can I make one comment about the previous question
yes.
by Takatomi-san? So there are some works on the estimation of support of density. And instead of using the real boundary, we could use the estimated support instead, or in combination with the support and the boundary. That may help to, we may neglect the region of zero density, basically. So we may not use the exact boundary of the city, but we may combine the method of estimation of the support.
That's a good point, because if you don't see many points, say around here or here, then you can just imagine the boundary doesn't exist or something.
Yeah, or we could estimate the support instead. Okay,
yes. So that's a very interesting suggestion. yeah, definitely I will think about it. Yeah.
Okay, then, well, if there are no other questions, it's probably time to close this session. Thank you everyone for joining us. We have one more session next week from ISM, so see you all next Thursday. Thank you very much.
Thank you. Bye-bye.
Bye-bye.